Hello Highlanders, we're back. 12.2, techniques for evaluating limits. So in this particular case, in 12.2, we are going to look at how we deal exclusively with holes. If you recall from 12.1, whenever we're looking for a limit, you're given a function, you're given an x value that you're trying to find the y value of that particular limit. What you want to do is first just plug it in. Take the x value, plug it into the function, see what you get. See what situation you're dealing with, because there might not even be a limit. If we have an asymptotic situation, there is no limit. Or you might just have a number, and you're done. Right? If the number's 5, like we had in our other example. But sometimes you get rational functions, so the dividing out technique is exclusively helping you eliminate that hole, right? Getting rid of that hole. So for example, let's say we have a function that is x squared minus 4 over x plus 2, and we are looking for the limit as x approaches negative 2 of f of x. So when x approaches negative 2, again, first step, plug it in, right? So what do we see when we take negative 2 and we plug it in? We're going to get 4 minus 4 over negative 2 plus 2, which is our indeterminate form. Again, that means we have a hole, right? That is our removable discontinuity. Because the 0 on top means that not only is this number a possible 0, it's also not in the domain, right? It's a restriction. So when you have a 0 and a restriction, that's when you know you have a hole. We should be able to remove it. So the goal in 12.2, what are those techniques? We're removing holes. Dividing out just means that we're going to do what? We're going to factor when possible. And in this case, we factor the x squared minus 4 into x plus 2x minus 2. And that, allowing us to factor, displays the common factor in the top and the bottom. So we remove it, hence the removable discontinuity, and we're left with x minus 2. So if we were to graph this, we would actually see this line, and it would look like this. Negative 2. And a slope of 1. And then what's happening at negative 2? Right. If we plug negative 2 into this function, we see the 0 over 0, but if we plug it into here, we get the actual value, and there's a hole there. So we get this as what we're seeing, right? So even though you look at that and you see that there's a square there, you think, oh, okay, well that's going to be some sort of weird rational function, but it's not, because of the removable discontinuity, because of the hole. So this is what actually gets graphed, and we jump over this, right? So what is the coordinate of that particular hole? Plug in negative 2 here, we get negative 4. So in answering our question, what is the limit as we approach negative 2 from the right and from the left, we get that y value is what we're approaching. Even though that y value is not part of the range, right, because it's a restriction, it is the limiting value that we are approaching. So to answer this question, the limit as x approaches negative 2 of f of x is negative 4. Which, again, all we're doing is finding the y value of the hole. Okay. Another example. Example number 2. Let's see here. Say we get x minus 1. Here's my function. Over x cubed minus x squared plus x minus 1. And we're looking for the limit as x approaches 1 of f of x. So again, first step, plug in 1. We plug in 1, we get 0 over 0. So that immediately alerts you to the fact that you need to find and destroy the hole. You've got to remove the hole. So, look to factor. Can I factor this? Well, that's one we're going to have to do by grouping. So I'm going to go ahead and group that. Factor out the x squared. So I got x minus 1. Factor out the x minus 1, and I get an x squared plus 1. So by factoring, we reveal the whole factor, which is that guy and that guy, so we remove it, and we're left with 1 over x squared plus 1 is the reduced fraction. And then to find the limit, plug it in. And so at 1, this function is going to be approaching this y value, which is 1 over 1 plus 1, or a half. So that is your limit. As x approaches 1 of f of x. So we see that if it's factorable, factor it. Another example. Let me see here. Okay. So we get the limit as a approaches negative 4 of a cubed plus 64 over a plus 4 . First step, plug in negative 4. So negative 4 cubed is negative 64. And then negative 4 plus 4. So again, and that's what you're going to be dealing with most of the time. But again, remember, you have limits other than this. So let's not forget, if I plug in this number and I get a number here, I mean this could be 7, then that's your limit. So, pay attention. And if you get weird types of piecewise functions, you got to make sure that you check them both, or all three of them, till they're all going to the same value to have an overall limit. You bring in absolute values and square roots. Sometimes you get domain issues that are going on too, so you just got to kind of pay attention to that. But in 12.2, this is kind of what we're focusing on right here, because that's the main guy. All right, so because it's 0 over 0, that must mean that this is a factor of this. So the reason I picked this example is because I wanted to remind you of how we factor the sum of two cubes. So the first factor is the cube root factor. So the cube root of a cubed is a, and the cube root of 64 is 4. And then coming off of that factor, square the first term, opposite product of the two, square the last, and then what we see, there's your hole. There's your removable discontinuity. So we remove that, and then to find the limit, we're going to plug in the negative 4 to what we have left. So negative 4 squared minus 4 times negative 4 plus 16 is 48. And that's your limit. So using all these algebra factoring techniques allows us to remove the holes when we have them to find the actual limits. Okay. If this was something that you couldn't factor, but you got 0 over 0, then that tells you that this is a factor of this. And if you don't know how to factor it, your other option is synthetic division or long division, right? So you can always do your division to divide out a factor. Factoring is obviously quicker. All right, next example. I'd like to go back to one that we had in the 12.1 notes, that we found the limit of. So it was this function and we were looking for the limit as x approaches 0 of f of x. And if you remember, we used a table to find that limit, and we ended up with 4. Now I'm going to show you how we can do this algebraically so that we don't have to use a table. Before we do that, first step, I keep saying this and I'm going to keep saying this, plug it in, right? Take the 0 here that we're looking for, plug it in to make sure we have a situation where there is a limit. So we get 0. Plugging 0 in for x gives me the square root of 4, which is 2. So there is our indeterminate form again, the 0 over 0, which means we have a hole. So we're going to go ahead and take our function that has a square root in it, and the way to get rid of the hole with the square root is to rationalize. So whether the square root's on the top or on the bottom, you're going to rationalize it. Which means, in this case, multiplying the top and the bottom by the conjugate. Right? And this is why we practice this. This is why we do this, for this very reason, so that we can get rid of the hole that's lurking here. So we're going to take and multiply the top and the bottom of this particular function by the conjugate of the denominator. And let me say this one more time. This might be here, or it might be here. So wherever that square root is, you need to rationalize it. So sometimes you're rationalizing numerators, sometimes you're rationalizing denominators, but we're going to use the conjugate here. So the square root of x plus 4 plus 2, the square root of x plus 4 plus 2. Again, there it is. One in disguise. I want you guys to forget about him. So on the top, we have x times the square root of x plus 4 plus 2x as we distribute here. And on the bottom, because they're conjugates, we don't care about our oi. We have x plus 4 minus 4, which leaves me with, I guess I probably shouldn't have distributed that. Broke my own rule, right? Remember, don't multiply until you have to. That's okay. So the 4's cancel. We're left with this. So now what are we going to have to do? Refactor out that x, which is why we don't multiply until we have to. But you see, by using the conjugate, by multiplying and rationalizing, what we have done is we have shook out this hole. So now we can reduce, and we're left with this. So to find the limit as x approaches 0, plug that in. And what do we get? The square root of 0 plus 4 plus 2, which is the square root of 4 plus 2, 2 plus 2, or 4, which is what we said when we looked at the table. Merely guessing there, but here we see that that is the actual y value that we are approaching in this particular limit. All right, another example. And again, as you're going through this video, when I write the examples down, anytime you wish to pause the video, do the example yourself, come back and see if it matches what I'm doing. I think is a really, really good way. It's how we would do things in class, right? That's how I would get you guys involved. So, practice that at home even though you're by yourself. So, next example, let's see what we got here. We got f of x equals the square root x plus 2 minus root 2 over x. And we're looking for the limit as x approaches 0 of f of x. So again, first step, this would be time for you to pause and see if you can do it. But the first step here is to plug 0 in, and we get the square root of 2 minus the square root of 2 over 0. So when you see that indeterminate form, we know what we have, right? We know that there's a hole, and because there's square roots involved, to shake that hole out, we're going to go ahead and rationalize the numerator. So I am going to take my binomial here, and I'm going to multiply the top and the bottom by its conjugate. So again, multiplying by 1 as to not change the value of the fraction. And when we FOIL the top, remember, because they're conjugates, there is no OI, just the first and the last. So we get x over x. There goes your whole. So we're left with 1 over that. So again, then to find the limit, all we do is we take our x value, plug it in. Again, looking for the y value of the whole. That's all we're doing here. So we get 1 over the square root of 2 plus the square root of 2, which is 1 over 2 root 2. And just leave it. No need to rationalize that. But that would be the limit. That's the value that we are approaching when we let x go to 0. Okay. So two techniques, right? Factoring / dividing out to find to get rid of the whole. And if you have square root functions, we're going ahead and we're using the conjugate to rationalize to shake out the whole. Another example. Let's bring in some trig functions. I guess before I do that, let's just take a look at one more algebraic technique here. Let's see, we got 1 over x plus 1 minus 1 over x, and we're looking at the limit as x goes to 0. What happens if we have a complex fraction, like we do here? And again, you're just going to rely on your algebra skills. We're going to go ahead and we're going to simplify this numerator. But before we do that, what do we always do? Plug in the number, right? So plug in 0, which gives me 1 over 1 minus 1 over 0, which again is 0 over 0, which tells me I have a limit. Just to review, had I plugged in something here, like let's say this was 2. Plugging in 2 would get me 1/3 minus 1, which is 2/3, negative, right? Negative 2/3 over 2, which is negative 1/3. And that would be your limit, and you'd be done. So again, the limit can be a number. It doesn't have to always be this indeterminate form, but because 99.9% of the time we are going to be working with derivatives and integrals, and that is the guy we're looking for. We want that indeterminate form, which leads to our difference quotient, which we're going to bring into this lesson again. Okay, so now that we know that we have a whole, we have to find it out. We do that by simplifying this, so we're going to get a common denominator. Take care of my negative sign. So I'll multiply by x plus 1 over x plus 1 over x. And then we can add our fractions together, making sure I take care of that negative. So I have 1 plus, and then this becomes a negative x minus 1 over x plus 1. And over x means I'm going to be multiplying by 1 over x. Simplifying further, those cancel. So I get negative x over x plus 1 times 1 over x. And now we can see where the whole is. So we can get rid of that, and we're left with -1. So that is my reduced version. And now I can go ahead and plug in my 0 to see what my limit is. And there it is. So sometimes you have complex fractions. Again, just simplify them. Get your common denominators. Be careful with your negative signs, and the whole will shake out. So sometimes we factor, and you can tell by looking at it. If it looks like you need to factor, that's what you'll do. If it's a complex fraction, just go ahead and simplify it. And if you've got square roots, you're going to multiply by the conjugate. Okay. How about some trig functions? Let's take a look at that. So here's another example. Let's say we have the limit as x approaches pi of cosecant x over cotangent x. And just because we're dealing with trig functions, nothing's different. You're going to go ahead and plug in pi. So we get the cosecant of pi over the cotangent pi. And the cosecant of pi, remember that's 1 over sine, and the sine of pi is 0. So we have an undefined over an undefined. That's another very special case of the indeterminate form when it's undefined over undefined. So what we need to do here, because we can't just do this directly, we're going to go ahead and yes, you can always build a table, but we're going to see if I've got some identities here that might help me do something. So I'm going to change cosecant into 1 over sine pi, and cotangent is cosine pi over sine pi. And what we see is what's creating the undefined over the undefined is the sine of pi. So we can remove it, just like we did with the whole. So using the definition of these trig functions, we're allowed to get rid of the sine, which leaves me with 1 over the cosine of pi. And the cosine of pi, remember, is -1. So 1 over -1. So there is your limit. So again, sometimes if it's undefined over undefined, we can use, sometimes we got to use our definitions, sometimes we can use our trig identities, all that good stuff. Another example here. Let's say we have the limit as x approaches pi over 2 of 1 minus sine x over cosine x. And first thing we do, plug it in. So the sine of pi over 2 is 1. So we get 1 minus 1. Cosine of pi over 2 is 0. So here we have, again, that indeterminate form, which means there's a hole here somewhere. And in this particular case, if I want to turn sine into cosine, if we're going to cancel something out, you're going to need to turn one trig function into another that is the same. And so you have that whole arsenal of your identities, your Pythagorean identities, your definitions, your cofunctions, everything here for your use, right? So what I would probably do here, recognizing that I can turn this into a cosine squared, because what's causing the problem here is this guy. So I'm going to multiply the top and the bottom by the conjugate. Again, we use a lot of conjugates everywhere, which is why I've been harping on those all year long. So we multiply by 1 in disguise. And what does that do for me? That gives me 1 minus sine squared up top. And 1 minus sine squared is cosine squared, your Pythagorean identity. And then we can get rid of that. So we're left with cosine x over 1 plus sine x, which is an equivalent form. Now we can plug in pi over 2. Cosine of pi over 2 is 0. And the sine of pi over 2 is 1. So we end up with 0 over 2, which is 0. So that is our limit. So this particular function here has a limit at 0 when we go to pi over 2. If we were to flip this around, that would flip this around and we would get 2 over 0, which the limit would not exist in that case. So remember, plug in the number. If you get a value for y, that is your limit. If you get a 0 over 0, or in some cases an undefined over an undefined, then we have the opportunity of trying to eliminate what's causing the 0 over 0 problem, or the 1 over 0, 1 over 0 problem. And then we remove the whole with one of these techniques, which gives us our limit. Or we get a situation where we have like a 2 over 0 that's asymptotic, which means limit does not exist. Okay, last thing here, I want to revisit our difference quotient. Because moving into 12.3, which is what we'll do next week, it's all about derivatives, people. So the difference, quotient, did I spell that right? I don't know, close enough. You guys know what I'm talking about. So the difference quotient, right? Remember, was this: f of x plus h minus f of x all over h. So a little refresher, because we did this so long ago, and we touched on it a little bit a while ago, but it's so important that I want to make sure that you understand where this is coming from. So you all know this, your slope formula. Change in y over the change in x. Right? That just finds the slope between 2 points, the rate of change between 2 points. And when we start talking about rate of change, that is what the word calculus means. It's exactly what it is. It's all about rates of change. So what we did to change this is we put it in its function notation. So y sub 2 is f of x sub 2. Y sub 1 is f of x sub 1. And then we let the change in x, we called it h. So keeping that in mind, h is x sub 2 minus x sub 1. So this is just a different look to that. It's the exact same thing. It's still just slope. Change in y over change in x. But the reason we do this is because, remember what we want to do. We want to go from 2 points on a curve to 1. Right? We want to let this go to 0. So to do that, we have to eliminate x sub 2. So to get rid of x sub 2, we go back to this equation right here, and we solve it in terms of x sub 2, or we solve for x sub 2 in terms of x sub 1 and h. So taking that to the other side gets me this. So then all I'm going to do is take and replace that with what it's equal to. So that is where the difference quotient comes from. And because these are the same, and don't forget, this x up here, we dropped the subscript because there's only one of them, but it is the x sub 1. It is the location on the graph whatever the function happens to be, but it is the x location on the graph that we are looking to find the rate of change at. So we're really talking about slope at a single x point. And in this case, this overall quotient is determining that slope. So it's a function of slopes. And because this is here and here, there's always going to be a hole. So when we talk about the definition of derivative, and we'll revisit this, derivative just means instantaneous rate of change or slope at a point. And because we cannot let this go to 0 physically, we have to look at the limit as h goes to 0 of the difference quotient. This is your definition of a derivative. So that being said, let's say f of x is the square root of x plus 5. And we want to find the difference quotient using this particular function. So the difference quotient then would be what? It would be f of x plus h minus f of x all over h. So in this case, using this function, f of x plus h means we're plugging that into there. So we have the square root of x plus h plus 5 minus f of x, which is the function itself, all over h. Now, based on what we've done, the work we've done, what if we do this? So recognizing that you have a square root involved, the way to get rid of that hole that's there, right? So if we plug this in, we're going to get x plus 5 minus x plus 5. And that's where this is always going to be 0, and this is always going to be 0. So you can take a moment and look at this, right? Because all we're doing is adding x plus h into here. When I let h go to 0, this function, right, if I let h go to be 0, this function is always going to be the same as this function. So you're always going to get a 0 on top, and you're always going to get a 0 on the bottom. So when you apply the difference quotient to whatever function you're dealing with, you're always going to get the indeterminate form, which is why it is so important, because it leads to our derivative, which allows me to check the instantaneous rate of change at a single moment. Critical. Okay, so using our techniques, what do we do here? We multiply the top and the bottom. By the conjugate. And again, we're not going to distribute that h this time. We're going to follow Mr. Lampkin's own rule. Don't multiply until you have to. Write that out. And again, since these are conjugates, first two, x plus h plus 5, minus the last two. Be careful with the negative sign. And remember that if your hole doesn't shake out here, you've algebraically done something incorrect, because it has to. So x minus x, 5 minus 5, all we're left with is the h on top, over the bottom, and there goes your hole. So we have x plus h plus 5 plus the square root of x plus 5. Now we're not rationalizing because what are we going to do now? We're looking for the limit, right? We remove the whole, we remove the 0 over 0, which was causing us the problem. So now I can go ahead and plug that in for h. And I get 1 over root x plus 5 plus root x plus 5, which is 1 over 2 root x plus 5. So what does this represent? That represents what we call the derivative of this particular function up here, right? That's the function it's tied to, and that's why we call it a derivative, because it's tied to that. It's a derivative of that. It's a subspecies of that, if you will. But again, where that is a function, right? If you were to plot this, it would look like, here's negative 5, it would look like that, right? That's the graph. So these are all the xy points here. This does what? This tells me what the derivative is, or the instantaneous rate of change of any tangent line along this curve. So for example, if I plug in 1, so let's plug in 1, I'm going to get the square root of, so that ordered pair location would be 1 root 6. If I plug in 1 into this function down here, I'm going to get, f prime means the derivative, so plugging in 1 gives me that number. What is that number? Again, this is a slope function, right? This is a function of slopes. So this particular tangent line has a slope of 1 over 2 root 6, which, to give you a feel for that, 1 over 2 root 6 is about 0.2. So at this point, right here, the slope of that tangent line is about 0.2, or that is the instantaneous, meaning happening right at that location. That is the rate of change on that graph. That's pretty powerful, because at any moment we could find what the rate of change is. And down the road, I mean, you recognize this as velocity. Velocity is the instantaneous rate of change. And when you step on that accelerator, your velocity changes, and that's known as acceleration. And acceleration is the rate at which the rate of change is changing. So we're going to talk about in 12.3 all about tangent lines, tangent equations, derivatives, but it all comes from doing the difference quotient, looking at the limit as h goes to 0, and every difference quotient, regardless of the function, right, is going to have that indeterminate form. Okay, I believe that is everything from 12.2. So that should give you everything you need to kind of go through and find your limits. In 12.1, using tables. In 12.2, using algebraic techniques to find limits of functions. Have a great day.